This class consists of three primary topics. They are matrices, linear programming, and probability. Matrices are an important tool, and in fact matrices will be used as a tool in the other two topics. So the first thing we need to learn is a little bit about matrices as a tool, and that's the subject of this movie. We'll begin to study matrices with the very simplest matrix operation, which is addition. But first, we need to understand what a matrix is. That's very simple. A matrix is nothing more than a rectangular array of numbers. Here we see a matrix named A. It's very common to name a matrix with a capital letter. This matrix has 2 rows and 3 columns, and so it's called a 2 by 3 matrix. Here's a matrix B, which has 3 rows and 4 columns. So it's called a 3 by 4 matrix. It's important to keep in mind that when you're talking about the size of a matrix, the common convention that's always followed is to list the number of rows first and the number of columns second. The way that matrices are added is exactly what you would guess. Here we have 2 matrices. Notice that these matrices are the same size. Each has 2 rows and 3 columns. And that's a cardinal rule. If you're going to add matrices, the matrices have to be the same size. That is, the same number of rows and the same number of columns. The way they're added is simply to grab the numbers from each matrix that are in the corresponding spot. To determine the number that goes into the row 1, column 1 position, we simply add the number from the row 1, column 1 position of the left matrix to the number from the row 1, column 1 position of the right matrix. 2 plus 5 is 7. Similarly, when we move over to the row 1, column 2 spot, we get 3 plus minus 4, which is minus 1. And if you follow through with the rest of the computation, this is what you wind up with. Let me remind you that when you're watching these movies, you always have a slider at the bottom which you can use to pause the movie anywhere you want to. So when you want to pause the movie to check a computation like this, by all means do that. Now, how would you guess that matrices are subtracted? Well, it's going to be the same way, and equally simple. Here we have 2 matrices that are the same size, and again, that's a requirement. And to subtract them, we just subtract term by term. For the first row, first column spot, we do 2 minus 5, which is minus 3. Moving to the next spot, row 1, column 2, we have 3 minus a minus 4, which is 3 plus 4, or 7. And you follow through all the calculations here to determine the difference of these 2 matrices, and this is what you should come up with. When are 2 matrices considered to be equal? Here's a simple example of 2 by 2 matrices, which involve the same numbers, but notice that the numbers don't appear in the same locations. Those matrices are not considered equal because the entries are not in the same locations. The left matrix has a 3 in row 1, column 1. The right matrix has a 1 in that spot. In the second example here, the 2 matrices are equal because the corresponding entries are equal. Notice that they're not written in exactly the same way. The row 1, column 2 position in the left matrix is written as 2, and in the right matrix it's 12 over 6, but of course 12 over 6 is equal to 2. So these entries are the same term by term, and that makes the matrices equal. So equality simply means they have not only the same numbers, but in the same spots. In this illustration, I'm adding two matrices, and notice that the second matrix has nothing in it but zeros. And since adding 0 to a number doesn't change the number, the obvious net effect is to leave the first matrix exactly unchanged. A matrix which is filled with zeros is called a zero matrix, and in this case we're looking at the specific situation of the 2 by 3 zero matrix, the zero matrix with 2 rows and 3 columns, all of whose entries are 0. And what we have observed is that when you add a zero matrix to another matrix, the other matrix is not changed. What do you suppose it means to multiply a number times a matrix? Here we have a matrix which has 2 rows and 3 columns, and we're multiplying it times the number 3. And you see that what happens is we multiply every entry in the matrix times 3. 3 times 7 is 21, 3 times 4 is 12, and so forth. So, in summary, multiplying a number times a matrix just means multiplying that number times each entry of the matrix. Let's do this problem, which involves a couple of operations. We have two matrices A and B. Each of them has 2 rows and 3 columns. And we're asked to determine the expression 2 times A minus 3 times B. So we're going to multiply each of these matrices times a number and then combine them in that manner. If you want to break this up into pieces, you can think of first checking out what 2 times A would be. Multiply each entry of A times 2 to get 2A. Multiply each entry of B times 3 to get 3B, and then subtract those two matrices. And if you do that, I believe this is what you get. 2A minus 3B, 4 minus a minus 3 is 7, minus 14, minus 6 is minus 20, and so forth. Here's a problem that involves some symbols which represent numbers that are unknown to us. We have 3 times the matrix on the left, which has 3 rows and 2 columns. And then on the right we have an expression involving multiplying 2 matrices times numbers and then subtracting them. So let's see what we can deduce about these unknown numbers. X. What do we have? We have an X, a Y, a Z, and here we have a U. So let's see what we can determine about those unknowns. Since the matrices are equal, notice we do have an equal sign here. It means that the matrix on the left has to have the same numbers in the same spots as the matrix on the right. Remember, that's what equality of matrices means. Now on the left, in the row 1, column 1 position, what we'll have will be 3 times Y when we multiply that out. On the right, if we calculate everything out on the right, we'll be multiplying 4 times this matrix, which will give us a 4 in the row 1, column 1 spot. And here we'll be doing minus 2 times minus 1, which will give us a 2. So we'll wind up with a 4 plus 2 when we calculate the row 1, column 1 spot on the right. And since the matrices are equal, that will tell us that 3 times Y, which is the row 1, column 1 entry on the left, will have to be equal to the row 1, column 1 entry on the right, which is 4 plus 2. 3Y will be 4 plus 2, which is 6, and of course that will tell us the value of Y. Move on over to the row 1, column 2 spot and go through the same logic, and you can deduce that 12 is equal to 4 times 4, 16, minus 2 times minus x, which is plus 2x. Now in this particular example, if you continue that process looking at the other spots in the matrix, you wind up with some contradictory information. That is, you wind up with a bunch of equations that contradict each other. They can't all possibly be satisfied no matter what the values of x, y, z, and u are. do that computation and see if you can recognize that. So in this particular instance, the conclusion you have to draw is that no matter what values you assign to the variables, the matrix equation can't in fact be true.